So up till now, the types of loads that we've looked at are point loads. And what's another word for point loads? Concentrated loads, right? So they're all loads that are concentrated in a certain point. But the topic that we're covering today is distributed loads. So here we have, this is a point load, or I could call it, remember I use this as an abbreviation for concentrated load. So it's concentrating right on a point. But what we're covering today is distributed loads. So if you go back to materials, and I know probably half of you took materials already, there was a time where you spread your load over an area. So you took some load force and you divided it by the area. And do you remember what that was called? It was called stress. And it was abbreviated sigma. That's sigma, right?
Yep.
Okay. Now, there's another word, those of you who didn't take materials have also heard of the word pressure. I think in materials it would have been clarified the difference between the two. But pressure is also force over area. But pressure is used for fluids, and that fluids describes air and liquid. So what would be an example? Water pressure through a pipe, air pressure in a bicycle tire. But when we talk about solids, we use the term stress. So what are some examples of units? Well, in the English system, an example would be PSI, pounds per square inch. Or how about kips per square inch? In metric, we might say newtons per meter squared, kilonewtons per meter squared. Okay, so this is dealing with force spread over an area. Spread over an area. But in statics, we're typically spreading our load over a length. So here we have a force, and we usually put a line over it. So you can see that they're all interconnected. This is a force over a length. And it's abbreviated little w. I think that might be omega. Okay, so force over length. So here's the length of, let's say it's a beam. We have a length of a beam, and we're spreading the force over it. So an example would be 100 pounds per foot. Here's my beam. And here's the force that I'm spreading over it. And let's say this is 4 feet. So in this example right here, I'm telling you that the force over the length is 100 pounds per foot, and we're spreading it over 4 feet. So what is the total load on this beam? It says 100 pounds per foot. Well, here's 1 foot. So in that 1 foot, there's 100 pounds. Another foot, 100 pounds. Another foot, 100 pounds. And another foot, 100 pounds. So if we think of this as an equivalent system, remember equivalent systems? Equivalent systems are another load diagram that shows the body with the same, experiencing the same thing, but it's simplified. So let's say in this case I have 44 feet, a 4-foot beam. And what can I do? I could take this, and it's 100 pounds per foot times 4 feet, and it comes out to be 400 pounds. So I know that this is equivalent to a point load of 400 pounds. But where should I put that 400 pounds? Well, we're looking at a rectangular area in a way. It's spread evenly. The force is spread evenly over this. So wouldn't it make sense that this 400 pounds should be in the center here? In a way, we're looking at centroid. Let's do another one. How about if I have a beam and I have my load triangular? And at this point right here, it's 400 pounds per foot. And it's 4 feet. Oh, sorry, let's stick with the 100. What we're trying to do is find an equivalent system, a 4-foot beam, that is going to be applying the same load with the same moment, actually. If we went back to this, at this point, on the leftmost point, I'm creating the same moment about this point as I would if there was a distributed load. This is creating the same moment at that point as this. So what is the moment here? It's 400. The moment at point O is 400 times 2. And is it positive or negative? It's negative, and it's inch pound. And that's the same moment that's created over here. Okay, so in this particular case, we're looking at a triangular load. And we're trying to figure out, we know that at this end of the beam, the left end, there's a 0 pounds per foot exerted right here. But over here, there's 100 pounds per foot. So we have to figure out how would that be distributed and how can we come up with a point load and where would it be located. So let's go back to this picture. I want to draw something that's equal. So I have this beam. It's 4 feet out, and it has a height. And this I'm calling my y-axis, and this I'm calling my x-axis. If this is the 0 point, wouldn't you say this is the 0.4, and this is in units of feet? Because it's spread over 4 feet, so it's going from 0 to 4. And what about this? This is 100 pounds per foot. That's really the height of this. So this right here is 100, and the units are pounds per foot. How would I find out what this area is in here? I would multiply the height times the base, right? So the area would be 4 base times height, and it comes out to be 400. So what we're really looking at when we do distributed loads is we're really looking at the area that's included where the distributed load is. We're looking at the length of the beam that it's subjected to and what the vertical value is, the W. So here's my W. So if we take that analogy and now we try to transform it to here, what is the total force on the system? If I think of it in terms of area, my force is going to be equal to the area. And what's the area of a triangle? 1/2 base, which is 4, times height, which is 100. So the force turns out to be 200 pounds. And maybe without me even going into the area, maybe you already figured this out. That if it's 0 on this end and 100 on this end, that probably the mid-range, which is 50, I take 50 and multiply it by 4, and I come out with 200 pounds. This is supposed to be an equal or a congruent sign on its side. So now we know I want to put my force, 200 here, to be equivalent, but where am I going to locate it? We have to go back to thinking about centroids and center of mass and center of gravity. When we have a triangular area, where is our centroid? It's 1/3 of the base from this fat end. So the equivalent here would be 200 pounds at a distance of 4/3 feet. So when we talk about distributed loads, we're really looking back at equivalent systems, and that's why equivalent systems is taught first, and then distributed loads is taught first. So we're taking a more complicated problem where there's a distributed load spread over a length, and we're coming up with a simpler equivalent system, which it has one point load at a distance. Same thing here. We started with something that was more complicated, it's a distributed load, and we're coming up with an equivalent system that's more simple, that's a point load at a distance.